So welcome to the second tutorial. We're going to be doing our first primitive on screen. We're going to be using um, a new library called Glue. We're going to be talking about some OpenGL concepts like vertex buffers, vertices, attribute arrays, and some other stuff. So let's begin, shall we? We're going to rename our solution to tutorial 2. We're going to want to specify some additional libraries, mainly glue.lib. I believe it's called glue.lib. And we're going to include, and I'm just going to make sure it compiles and links to get it. Yeah, see, it couldn't included before glue. Probably because glue wanted to be installed, wanted to be first to the scene. So cannot find glue. Can't remember what it was called exactly. Maybe it was glue32.lib. Yes, that seems to be it. Alright, so now that we've prepared build settings, I guess you can say, for this, we could begin with doing this. So, this is going to be our first encounter with Glue, the OpenGL extension Wrangler library. Glue helps you deal with the headache that can accompany the management of extensions in OpenGL. Once initialized, it queries for all available extensions on your platform and dynamically loads them and provides easy access via that single header file. In this tutorial, we will see the usage of vertex buffer objects for the first time. As the name implies, they're used to store vertices. Vertices are the objects that exist in the 3D world that you're trying to visualize, be it monsters, castles, or simply a rotating cube. They are always built by connecting together a group of vertices, so vertices are pretty crucial. VBOs are the most efficient way to load vertices onto the GPU. They are buffers that can be stored in video memory and provide the shortest access time to the GPU, so they're definitely recommended. So let's begin. Let's begin by initializing Glue. We'll increment this. Next up, we're going to be creating a new file, a header file to be exact. We'll include this. The 3D math is where we're going to specify some math for stuff. because we're going to need it. So the first step we're going to do is we're going to have a vec3 class, which is going to store 3 floats. It's going to have an empty default constructor, and it's going to also have a constructor that will initialize them. That seems like fairly simple, and we're going to include that into our process here. Next up, we're going to create a new function for preparing the render state. This is going to be responsible with creating our vertex buffer. For now, we're only going to have one vert. And we're going to specify 0, 0, 0, which is the center of the screen. Now comes the first part of vertex buffer objects. So let's begin, shall we? So OpenGL defines several GLGen functions for generating objects of various types. They often take 2 parameters. The first one specifies the number of objects you want to create, and the second is the address of an array of GL unsigned integers to store the handles that the driver allocates for you. Future calls of this function will not generate the same object handles unless you delete them first with GL delete buffers. Note at this point you don't specify what you intend to do with the buffers, so they can be regarded as generic. This is job for the next function. Bind buffer, array, buffer, render, VBO. So OpenGL has a rather unique way of using handles. In many APIs, the handle is simply passed to any relevant function and the action is taken on that handle. In OpenGL, we bind the handle to a target name and then execute commands on that target. These commands affect the bounded handle until another one is bound on its stead, or the call above takes 0 as the handle. The target GL array buffer means that the buffer will contain an array of vertices. Another useful target is GL element array buffer, which means the buffer contains the indices of the vertices in another buffer. Other targets are also available, and we'll see them in future videos. So after binding our object, we fill it with data. The call above takes the target name, same as what we used for binding, the size of the data in bytes, the address of the array of the vertices, and a flag that indicates the usage pattern for this data. Since we're not going to change the buffer contents, we specify GL static draw. The opposite of this would be GL dynamic draw. While this is only a hint to OpenGL, it's a good thing to give it some thought as to the proper flag to use. The driver can rely on it for optimization heuristics, such as what is the best place for the memory to be stored for this buffer. So in the shader tutorial video, you will see that vertex attributes used in the shader, position, normal, etc., have an index mapped to them that enable you to create the binding between the data in C++ and the application name inside the shader. In addition, you must also enable each vertex attribute index. In this video, we are not yet using any shader, but the vertex position we have loaded into the buffer is treated as vertex attribute index 0 in the fixed function pipeline. the fixed function pipeline, which becomes active when there is no shader bound. You must also enable each vertex attribute, or else the data will not be accessible by the pipeline. But for now, we don't do that since we don't need that for preparing it. We actually need this for drawing it, which we will do now. So here we bind our buffer again as we prepare for making a draw call. In this small program, we only have one vertex buffer, so making this call every frame is redundant. But in more complex programs, there are multiple buffers to store your various models, and so you must update the pipeline state with the buffer you intend to use. So this call tells the pipeline how to interpret the data inside the buffer. The first parameter specifies the index of the attribute. In our case, we know that it is 0 by default, but when we start using shaders, we will either need to explicitly set the index in the shader or query it. The second parameter is the number of components in the attribute, 3 for x, y, and z. The third parameter is the data type of each component. The next parameter indicates whether we want our attribute to be normalized before it's used in the pipeline. And finally, in our case, we want the data to pass unchanged. The fifth parameter, called the stride, is the number of bytes between two instances of the attribute in that buffer. When there is only one attribute, example, the buffer contains only vertex positions, and the data is tightly packed, we pass the value 0. If we have an array of structs that contain a position in normal, each one is a vector of 3 floats, we will pass the size of the structure in bytes, 6 times 4 equals 24. The last parameter is useful in the case of the previous example. We need to specify the offset inside the structure where the pipeline will find our attribute. In the case of our structure where the position in normal, the offset of the position is 0, while the offset of the normal is 12, because 3 times 4 is 12, because 3 floats for x, y, and z, and then after those 3 floats begins our normal, which are the next 3 floats. Finally, we can draw it. And it's always a good practice. It's always good practice to disable the attributes when you're finished with them. Otherwise, if they make it to a shader, lots of strange things can occur. Here we're going to tell it to create our data for us. I called it render prepare. That should be sufficient. And let's give it a compile. Everything linked. And as you can see, we have one tiny dot because we have one specific point. And it is exactly in the center of the screen. That concludes this tutorial.